Hello, everyone, and welcome to an episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to introduce physical geography, and then we're going to move our way right into geographic grids as a kind of introduction to maps here. So, without further ado, let's get going. So what is physical geography? And as you'll see, we'll move through this physical geography, Earth systems, and then kind of getting into geographic grids and different map projections. And in the following lecture, we'll talk more about maps. And then right away in the course, we're going to conduct a series of exercises during this course, and many of those, or several of those, integrate research and inquiry, and so I wanted to kind of just provide that information about what is research and scientific inquiry right away. So before we begin, how about take a moment, think about what is physical geography? Define it in your own words. Feel free to write it down or type it. Just kind of give it a second and think about what is it? What does it mean to you? You can brainstorm, even just list words, descriptions, etc. As you do that, maybe to emphasize, here's a picture I took of the Hoh River rainforest in the Olympic Peninsula of Washington State. If you ever have the opportunity to go to the Hoh River rainforest, I highly encourage you to do so. All right, so what is physical geography? Simply put, it is spatial analysis, so thinking about space, of physical components and natural processes. So the Earth spheres, four major Earth spheres, as we'll learn here shortly. But ultimately, we're thinking about energy from the sun as it affects Earth, and then how Earth systems then are essentially using and recycling that energy and how it's all interconnected. And so, as you'll see, Earth system interactions, we're going to really kind of emphasize the interconnectedness of Earth's four major systems. And then to kind of specifically tie that to spatial analysis here, a major part of geography in general, and then here physical geography, we're thinking about and quantifying, interpreting, analyzing space to explain patterns or distribution, whether that be of certain plant species or even human migration or atmospheric conditions. And so we're using spatial analysis to explain physical space. All right, so to emphasize the interactions here, we're going to first define what the four major spheres of the Earth system is or are here. And so the four spheres are atmosphere, lithosphere, hydrosphere, and biosphere. And so I'm going to take a moment here to define each of these. But before we get to the definition of each, I do highly encourage you to use this link right here, click link, and open this Big Idea 3 Earth Systems Interact video. So go ahead and check that out. It's a great kind of introductory content, only a handful of minutes long, thinking about Earth systems science and physical geography. All right, so what are these four Earth spheres? The first one is the atmosphere. It is a gaseous layer that surrounds Earth, and it is essential to life. So it's essential to us, and it's largely composed of oxygen and nitrogen, as well as carbon, among other compounds and constituents. And then moving down, so to speak, into the lithosphere, which is the solid layer that encompasses the outer 70 kilometers of Earth. So this includes both soil as well as solid and unconsolidated materials. We'll dedicate some time later this semester to thinking about geology and physical geology. The hydrosphere, I want to say it's my favorite, but I'm not sure they're all kind of my favorite. I was, in fact, and still am very much a hydrologist, so I've spent a big portion of my life, both professionally and just for fun, thinking about living and experiencing the hydrosphere, which is water in all forms, where it flows and how it's stored. So we'll come back and think more critically about the hydrosphere later this semester. And then last but not least, the biosphere, which is the living portion of Earth. It includes both plants and animals. And really kind of throughout the entire course, we're going to think critically about the biosphere and how the biosphere interacts with each of these major Earth systems, as well as emphasize a portion of the course directly toward the biosphere. So here's our kind of breakdown, if you will, of the four major spheres. We have air as atmosphere, water as hydrosphere, life as biosphere, and land as lithosphere. And then within the physical geography, there are many subdisciplines. This is just a handful of all of them. But here is kind of how some of these sub-scientific disciplines fall. So climatology and meteorology encompassing the atmosphere, and geology, soils, geomorphology, the lithosphere, ecology and biogeography, the biosphere, and then here hydrology. There's even subtopics of ecohydrology and micrometeorology, etc., thinking about these interactions. Okay, so there's just kind of a general introduction to what physical geography is and where we're headed this semester. Really, we're going to spend time in each of these four major spheres, the four major sections of the course, and then we'll kind of think more into these subdisciplines. Before we do that, and then thinking really about the definition of physical geography, we need to know about space, and we need to be able to use spatial analysis to explain physical properties and processes. So to begin then here, we're going to simply think about geographic grids, which then allows us to understand more about spatial analysis and mapping, really. And so space and mapping would be so much easier if the world were flat, or still flat, right? As we used to believe. Anyways, the Earth is most definitely not flat, but if it was, it would be a lot easier to map. And so because Earth is a three-dimensional object, we need to depict that three-dimensional object in a two-dimensional space in order to analyze it, because it's kind of hard to just walk around with a globe all the time. So here, let's kind of think about globes and spheres and then kind of move our way into how this is projected into a two-dimensional space. And so our Earth really is divided into a series of circles in terms of how we grid it to subdivide it. You can call a great circle as any circle that perfectly bisects Earth into equal halves. And so, as you'll see in a moment, the most easy or the most common example actually of a great circle is the equator. So I'll come back to that. But we also use small circles to subdivide Earth. And so common examples of small circles using to not bisect, but kind of subsect, if you will, Earth would be the Arctic Circle or the Tropic of Capricorn in Cancer, the Antarctic Circle, for example. And really here are lines of latitude, as I'll describe in an upcoming slide. So we have great circles and small circles. And so lines of longitude are lines that run north and south, and we use them to determine our location east and west of the prime meridian. And so, as I said, they run north and south, and they're also known as meridians. So any line of longitude is a line of meridian, or is a meridian, and the prime meridian, 0 degrees longitude, happens to pass right through Greenwich, England. And so our 0 degree longitude line here, meridian, passing, as literally in this picture showing, directly through Greenwich, England. And so then we, in terms of grids, use it to determine our relative position in degrees east or west of the prime meridian. So kind of going out and away, west or east of the prime meridian. Kind of some additional information, more longitude, as you will, measurement and mapping. So in this case, the greatest distance between any two lines of longitude, so between 0 degrees and 1 degree west, for example, the greatest physical distance on Earth's surface is right at the equator because it's a sphere. And in fact, every single line of longitude interconnects at both the North and at the South Pole. And so at that place, actually, there's 0 distance between all of the lines of longitude. And as you can kind of see in this picture here, the distance is greatest at the equator And as you get closer and closer to the North Pole, that distance between those same two lines of longitude, like 0 and 1 west, is getting smaller and smaller and smaller until they actually all just interconnect there at each of the poles. Okay, so moving on, lines of latitude. They run east and west, and they are used to measure your position relative to the equator. And so these lines here, as you can see, they're running east and west or horizontally. They're called parallels because they're literally parallel to each other. It's like you cut an orange and you perfectly slice it and slice it and slice it, and all those slices are stacks that are perfectly parallel to one another. And so then the great circle, being the equator here at 0 degrees, is the line of latitude that perfectly bisects Earth in half, separating the northern hemisphere from the southern hemisphere. So one step ahead of myself, the northern hemisphere and the southern hemisphere as subdivided here by the equator, just kind of another way to look at that. So a little bit more latitude, if you will. In this case, because they're parallel in the way that if you like were to slice a perfectly spherical orange, for example, as you slice it, the distance between any two lines of latitude, so in this case, between 0 and 1 degree, is exactly 111 kilometers. And then if you go between 1 degree and 2 degrees, that's also exactly 111 kilometers, and so on and so forth, all the way up to the pole. So between 89 and 90 degrees, that distance on Earth's surface is exactly 111 kilometers. And so there's a consistent distance between every single degree line of longitude. Um, we then kind of put them together, lines of longitude here running north and south. Here's our prime meridian, and lines of latitude running east and west. Here's our equator at 0. And so we're now going north, lines of latitude. So here's 30 degrees north, 40 degrees north, 50 degrees north. And then we're going to go lines of longitude running west and east of the prime meridian. And so I put an X right about here. Anyone know where that is? Do you know where that is? Well, it happens to be Marquette, Michigan. So where is Marquette, Michigan? Are we in the northern or southern hemisphere? So here we're in the northern hemisphere. We're going to go up to 10, 20, 30, 40. It's north of 40, and it's actually south here of 50. So it's somewhere between the two. And then we're going to move our ways west, and we're going to follow these lines. And then to kind of demonstrate that, specifically, we are exactly 46.5 degrees north of the equator, and we're exactly 87.4 degrees west of the prime meridian. So that's essentially, or that is how you determine your location anywhere on Earth. And so you can kind of use this screen here to practice that, whether it's south, we can go down 20 degrees south, and then you could kind of follow the lines to see some location in the Amazon, for example, to see if you're what line of latitude, how far south of the equator, and then how far west of the prime meridian, or here would be east of the prime meridian. Okay, so that's the basics of latitude and longitude. We'll come back and kind of reintegrate that into some future map content. But here, another way, at least here in the US, that we've subdivided space was through what is known as the US Public Land Survey System. And so who were the US Public Land Surveyors? And what was the point? And so before the 1800s westward expansion, as it's known, really land in the what is now United States of America, so land in the US was subdivided using a method called meets and bounds, which is kind of inherited from Europe and England. And that really was like take 27 paces in this bearing and then go to the rock. And then at the rock, you go 112 paces and then back to the river. And then essentially just kind of like subdivided space. But there was no real grid or any sort of kind of like system to that. So meets and bounds didn't really work. What if that rock went away or the river kind of changed? And so here comes the public land surveyors. Who were they? Essentially, they went across with survey equipment, so with levels and with survey rods, and they made perfectly north and south and east and west gridded lines across all of the lower continental US, rather, to subdivide it into a series of smaller and smaller and smaller squares. At least locally, one of the more famous public land surveyors was the very own Douglas Houghton, who, where the town of Houghton is named after. He was a public land surveyor here up in Michigan as well as other places, but he was largely credited with discovering copper in the Keweenaw, which then led to the very significant copper boom or copper rush in the Keweenaw, where there was a lot of mining activity in the middle to late 1800s and early 1900s, kind of tying back to some of these notes recorded by the public land surveyor known as Douglas Houghton. Okay, so what are the details of the US PLS, the US Public Land Survey System? This was the primary land is subdivided, and it is a grid system, really, again, kind of squares. Think about sequentially smaller and smaller squares gridded out across the US using the four major cardinal directions. So to date, over 1.5 billion acres have been surveyed, and this is the primary way of the legal description of land. Literally, if any of you have bought or sold, or perhaps some family members own a 40-acre parcel, or any amount of land, really, for that matter, if you go to your county courthouse to get the legal description for that parcel, it includes this U.S. Public Land Survey System description. So that's what we're going to work through next, is how is this subdivided and how is it written out? How are these legal property descriptions? How do they work? So your first step is to define the principal meridian. So remember, a meridian is a line of longitude running north and south. And so those principal meridians are tied to some specific line of longitude. And so the first step is to define that. And so what they did across the US is they have a series of different principal meridians. I'm going to go back, and you can see here's one principal meridian, here's another one, here's another one, here's another one. There's several or more dozens of principal meridians. So your first step is to determine which principal meridian your land has been referenced to. And so here, this is the Michigan meridian. If you zoom on right here, it says Michigan meridian. And so our first step is to determine the principal meridian. And then the second step, I did not create this. This is how it works. From that grid, actually, as the legal description is written, you would actually go from smallest grid to largest grid, as I'll show you here in a moment. So the smallest grid system is a series of quadrants that are subdivided into up to 3 quarters. And so using those cardinal directions, the goals are to take your smallest square and then work out to your next biggest square. And then finally, some have 3 levels of subdivision. For example, here is one square, and it's subdivided into 1, 2, 3, 4. We're focused on this gray square right here, which is in the north and west quadrant of this next largest square. And so here's the northwest quadrant of this square. And now we're on the second subdivision, moving outwards. And the next step, then, we're in the north and the east quadrant of this next largest square. And so as you see, it is the northeast quadrant, sorry, the northwest quadrant of the northeast quadrant. And then you move, and this box is exactly 1 square mile. And so here you're subdividing into 36 square mile sections within a township and range, which I'll get to next. Be aware that this is 1 square mile. So 1 mile by 1 mile, and section 1, 2, 3, 4, 5, 6, and then it literally zigzags within this square it goes 6 and then 7 to 12, 13 to 18, and it just kind of keeps going back and forth until you've reached 36. And so each township and range then is 6 miles by 6 miles. And so the next step would be to determine your section number. So we're in section 25, which that step is pretty straightforward. You literally just determine what square you're in. And then in this case, we're in section 25. And then finally, last but not least, we're going from smallest to medium to largest. We need to determine what township and range we're in. And so this works. You find the corner. So in this case, where my little laser pointer is the corner. Every principal meridian only intersects one baseline. And so the baselines aren't labeled because there is only one baseline for every principal meridian. And so there's only one X, so to speak. And so you always start from the middle of that X, and each of these township and ranges, again being 6 miles by 6 miles, move as a quadrant, a grid moving north or south, and then east or west. And so you go here, township, we're going to go townships to the north and ranges to the east and to the west here. And so if you go township 1 north, township 2 north, township 3 north, et cetera, et cetera. And then here moving left to right or east to west. So here moving east. So range 1 east, range 2 east, range 3 east, et cetera, et cetera. And it keeps moving out from there. And so this gray shaded box is in township 1, township 2 north, range 1, range 2 east. And so abbreviated, and then your legal description, literally at the county courthouse for any parcel, for this parcel specifically, would be the Michigan Principal Meridian, which is in the northwest quadrant of the northeast quadrant of section 25 within township 2 north and range 2 east. So one more time, and to kind of go a little bit faster, to link it in a different way. Here, also thinking about the Michigan Meridian. So here we're going to once again reference this corner. We're in the Michigan Meridian. This case, we're down here lower south of that X. So the next step again would be to go from smallest and then moving up through the quadrants, the quarters, and then to the next medium size, the section, and then to the township and range. And so right here, you have the south. So I'm going to find, here's the square we want to look at. Here's the next biggest square, and we have the southwest quarter of the north, of the southeast quarter, of the northwest quarter of section 11, township 2 south, and range 5 east. And so here's township 1 south, township 2 south, and then we have our ranges. We have range 1, 2, 3, 4, 5. And so that's to the east. And so altogether then that description is as present on the screen. All right, so that's enough about grids. Let's talk a little bit about map projections. And so here, just checking something there quick. So I clicked on something. Apologies. There it goes. Okay, coming back. There we go. So now we're going to think about how three-dimensional Earth or a three-dimensional object is projected onto a two-dimensional space. And so here, maps are a primary tool used with geography. Every professional quality map includes a theme, some geographic information, a scale here, and a legend to determine what you're actually interpreting or looking at. And so the practice of cartography is the design and production of maps. While you can make a physical map, we often, or most all maps now, are made digitally using interactive softwares like ArcGIS or Esri, and these softwares then allow us to make these professional quality maps as a cartographer and then potentially print them out and use them. Okay, so let's think a little bit about map projections. So what is the most complete and accurate way to represent the Earth? It would be a sphere or a globe, but that is kind of hard. And then if you're looking at a computer screen or digitally mapping, you would actually have to have like a three-dimensional sphere to achieve that. And so then here we need to project this three-dimensional Earth onto a two-dimensional surface. But there's not just one way to achieve that or to do that. And so be, because it's a sphere and we need to project it on a two-dimensional space, you really often can only preserve one variable, being size or shape, at a time, while some projections have attempted to preserve both. They look a little funny. And in fact, you can kind of like peel an orange in this way if you do it right. But here, Good's homologous line is one method in which both shape and size have been preserved. However, you probably would agree that it's not very common. We don't often use this projection, as it is a lot more common to see a map like Google Maps, for example, that looks more something like that. And so again, we're going to project or represent three-dimensional Earth onto a two-dimensional surface. And so in this case, one of the most common projections is called the Mercator projection. I'm sure, and whether you realize it or not, we have all seen or used the Mercator projection. It is often in things like Google Earth or Google Maps, many of kind of online softwares, et cetera, any sort of map. Many of them use the Mercator projection, which maintains the correct shape, but it distorts relative size, especially toward the poles. And so this relative amount of distortion is greatest toward the pole here, where Greenland has the correct shape, but it looks a lot bigger than it really is relative to especially locations nearer the equator. So here's the Mercator projection, a really useful and commonly used projection system. Another projection is called the Albers projection. And in this case, it kind of is like the reverse or inverse, where it accurately portrays size features. However, shape is distorted. And then similarly, that shape has the greatest amount of distortion nearest the poles. Again, because we're thinking of this three-dimensional sphere. And so Albers high latitude shapes are distorted, but their relative size is preserved. A third projection, which is also very common with many of our mapping systems, including Google and other platforms, is called the Robinson. And this actually does attempt to do both. It doesn't do either one perfectly, size or shape, but it kind of tries to balance the relative amount of distortion of size and shape so that they are relatively good, so to speak. And so the Robinson projection actually distorts both size and shape, but it does so in an attempt to balance them out. Okay, so now we're going to move on, and really the next handful of slides are kind of more intended to like set the tone or set up future lecture exercises, participation activities, etc. And so within this semester, as we are in a physical geography introductory level science course, we'll be conducting scientific research and inquiry. Some of these exercises, we're going to collect observational data. I'm going to even have you make a hypothesis and then test said hypothesis. So what is all this terminology? Let's just learn a little bit first. So what is science? Science is the intellectual and practical activity encompassing the systematic structure and behavior of the physical and natural world. And really, as you'll see here in future slides, we use observation and experimentation to better understand this systematic and structural behavior. So, oops. Research specifically, and here's a couple pictures of me conducting research over the years, but the systematic research is a systematic investigation, and it's done to establish new facts or reach a new conclusion. And so often, or research is an endeavor to discover something new, or at least organize old facts using what is known as the scientific method. More on that in the next slide. And so really, it's a systematic investigation to discover new facts. So how does this work? So often, or at least here within what is known as the scientific method, a scientific investigation begins with observation, like literally look outside, look around you, observe the natural and physical phenomenon around you. And then based upon those observations, you pose a question. So that's first step, observation and then question. From that question and your observations, you propose this kind of like causal explanation, some sort of explanation. And really, that is or takes the form of a hypothesis. So we'll define hypothesis in a future slide, but really, a hypothesis is a causal statement, a statement containing an explanation. So then hypothesis testing is done by making further observations or conducting experiments. So from those observations and experiments, we organize these data into results, and then use that to either confirm or contradict or to test the hypothesis. And so based upon the testing of the hypothesis using your observations and your results, you then, as a scientist, as a researcher following the scientific method, come into some conclusions. You draw conclusions based upon these results, which then leads you to either ask new questions if your hypothesis was supported or confirmed to like further knowledge, or perhaps if it's discarded, it comes back to observation and re-questioning to kind of restart the scientific method over. All right, so to provide a couple definitions of these terms, what is a hypothesis? It is a tentative explanation or description that can be tested. And so it has to be a yes or no, so it doesn't necessarily need to answer why, but it does need to be answered as yes or no. And so it needs to be tested. A theory then is an idea or system of ideas explaining a phenomenon. And so this then we're following general principles of physics, science, etc. And so then these theories are ideas explaining phenomenon, whereas a law is a description of a regularity, something that holds true. It's a statement in specific instances. It does not answer why. However, it is a statement that we follow, and really kind of like some of the theories are guided by laws then. So an idea or system of ideas explaining a phenomenon. Finally, here a model, which I really like, and you'll see throughout this course, we will be either interpreting models or even creating them. So just a simplified representation of some part of reality, which I personally find really useful, especially when attempting to investigate or critically think about something very complex or potentially complex. I often find it's really useful to kind of simplify it into a box model, really, like how this is here and what happens to this. It goes here, it goes there. And so by providing these simplified representations, it often allows us as scientists to kind of ask more specific questions. So there's two major approaches to scientific inquiry and research. And so there's an inductive approach, which is where you start with an observation and then come up with a hypothesis. So your hypothesis is based on observation. Or there's the deductive approach, which is where you actually start with the hypothesis and then test to see if reality matches up with your expectations. And so inductive, starting with observation; deductive is where you start with a hypothesis. What are the goals of scientific inquiry? are really to describe the process, a relationship, a condition, the mechanics, the mechanisms of a system. And so they also can be used to predict. And so that's predicting. So it's using observational or past data to predict or forecast the future, often whether it's a relationship between temperature and humidity, for example, as we'll look at later this semester, or a comparison between two groups. And so predictions, this is often why we're doing it. And then ultimately it can be used as an explanatory tool or how to explain something. So why was group A, this type of tree, significantly different than group B, a different type of tree in terms of how they responded to water or temperature stresses or inputs? Could also be how does variable A, like amount of moisture, significantly influence variable B, growth of a plant? So here, these are the goals of scientific inquiry. And then last but not least, at least in this kind of very brief overview of scientific inquiry and the scientific method, often in science, we conduct science for the sake of knowing, which is basic science. And really, this is kind of to further our knowledge. It's to kind of expand on theories or to kind of enhance or expand on even a law or to determine kind of how laws do may or may not affect certain systems in different ways. So that's like basic science. It's the science for the sake of knowing, which is really useful. And then there's applied science, which I would say most of my science really falls into this category, which is kind of for the sake of solving a problem. It's very situational. Like, here's this situation. It might be there's an invasive pest like a beetle, like the emerald ash borer, which I spent many years, almost a decade, focused on, and it's going to come and it's going to kill hundreds of millions of trees. What do we do about it? And so we can test it. We can harvest some of these trees. We can look at how other trees respond. We can plant new trees and many different types of new trees and see how those respond to make kind of informed science guided decisions or to help decision makers with science guided support, if you will. And so this is applied science. And so I'll provide many more examples throughout the semester of applied science. And here are a handful of pictures that I've collected over the years, either taken or taken of me conducting applied science, and including here actually an NMU student, another NMU student. So I'll introduce those later. But for now, Dr. VG is signing off.